Hey everybody, welcome to my shop. It's a nice 3 degrees outside and in here, so you'll hear a little heater in the background. In front of you you'll see a couple of my older multimeters. I've had this one for probably almost 20 years. They're no longer available, but it's a great little pocket digital meter. And then this is a cheap one from the local Princess Auto that I've been using. But in my current electrical engineering and computer engineering degree that I'm taking, I found that I needed a new multimeter, and it just arrived. So we'll take a look at it and put it through its paces and see what it has to say. This is from banggood.com. I purchased this myself, and it is the ANEng AN8009. So it's an auto-ranging multimeter. You can see it's actually very small. It comes with one regular set of probes, and then this set of probes here has screw ends. Like that. I'll show it in the center here. Screw ends like that, so you can screw on different probes and make up whatever kind of probe you want to have. Alligator clips, these kind, banana plugs, spade lugs. Unfortunately, mine when it showed up, as you can see, doesn't have the banana plugs or the spade lugs. As soon as I let Banggood know, they refunded me $5 towards those, which is what a full set of these would cost on Banggood right now, is the $5 in Canadian. And it also came with this nice zipper case, basic user manual in English with all of the ranges and the basic operating instructions. Now this is the upgraded version of the ANEng 8008 that there are tons of reviews of on YouTube, and most of the reviewers have said that for a home hobbyist it's one of the best multimeters you can get. I got it on sale for 25 Canadian, and so far in my using of it, it has turned out to be an excellent meter. Compared to, say, this meter, which is a 4,000 count. 4,000 count means that in the digits here, this last digit only goes up to 4. It actually only goes up to 3999. And at that case, or sorry, this is actually even smaller. This is a 2000. So this actually only goes up to a 1 here. This is a 2000 count meter. This one is my 4000 count. So this only goes up. You notice the ranges are 220, 2000 milli, 200 milli. So this scale only goes up to a 1 here. You only have 3 digits. This meter is an actual 9999. You get all 4 digits will go all the way up to 9 before it ranges, and we'll take a look at that in a minute. But as they say on EEVblog, first thing you should do is take it apart. So we'll just do a quick disassembly there, and we'll take a look at what's inside. Get a little bail on the back here. Same kind of construction as in the 8008. This opens up and this will come apart. You can see this just slips on, and that screw is not captive, it will fall out, so I just keep this on there to keep it from falling away, and take out my cheap dollar store batteries. And that's in there good and tight. can see these are the same kind of self-tapping screws that were in the 8008. So you don't want to be taking this apart all the time. But this screw here has got the brass insert, because you're going to be taking that open and close quite a bit in order to get the batteries in and out. There we go. So it's the same kind of construction here, with just the metal tabs going to the inside with the plastic shell. Same kind of fusing, same kind of narrow space. Let me see if I can see that on there or not. Same kind of narrow spacing between the pads so that in high voltage situations it will arc. PTC still way up there. So it's the same basic layout as the 8008. You can see your current shot, your two fuses, very small fuses. But overall it has the same features and the same problems as the 8008. Now, why would I go for this one over an 8008, given that they're almost the same price? The two reasons I chose this one over the 8008 is that the 8008 has a couple holes in its capacitance ranges, so it jumps not just a decade, but a full 2 decades in between a couple of the ranges and capacitances, whereas this one does not. And the 8008 has a square wave generator, which I didn't think I was going to find much use for. And this one replaces the square wave generator with non-contact voltage measurement. And that's also a bit of a misnomer, because it actually doesn't measure the voltage as volts, so you can't really read how many volts are in it. It's more of a safety check to see if there's actually voltage flowing through the cable or not, so you'll know if it's hot or not. Doesn't actually measure it. It will give you a bit of a relative intensity, which we'll show you here in a bit, but it's not really a measurement so much as just a magnitude measurement. Alright, so there's a basic disassembly, and right now you can see that it's auto ranging. So in this range here you can measure volts, AC or DC, hertz, and duty cycle percentage. You switch those by using this yellow button here. So now it's in true RMS AC. We'll test that shortly. There's hertz, you can see up there, and duty cycle. Back to auto range DC. This mode here is millivolts, AC or DC, and it also does temperature. Put it up there, see we're millivolts, true RMS millivolts, degrees Celsius, degrees Fahrenheit. Back. This one here is your up to 100 mega ohm resistance, and you can see it just auto range through. A diode checker, continuity checker, and capacitance checker. So there you are in your continuity. You see the little belt, diode, and in farads. And back to the range. This is your frequency and duty cycle again. This is your AC or DC amps or milliamps, which uses this port over here. And this is microamps, also AC or DC, and it uses this one. So you can see here it says microamps. And this is your non-contact voltage measurement. Okay, all this is, it took me a while to figure out, this is probably says electric field. So if I bring over this cable that the light is running on, you can see it's picking up. There is some voltage there. So it's good for telling you if something is live or not, but that's about it. It seems to be up in this corner somewhere. Alright, so we'll set it up with my voltage supply over here, and we'll see what voltages we can measure. Now, I'll I'll just quickly show you what I'm using here as a voltage supply, because it's going to come in to another project I'm working on. This is my briefcase full of stuff, including this NRI Discovery Lab. Now, Elnico is the actual manufacturer of this, and you can see that it has AC in, and it gives me ground, minus 12, plus 12, plus 5 volts. You probably can't see that on there. Let's just move this out a little bit so you can see. There we go. Ground, minus 12, plus 12, and plus 5. It also has a 0 to 20 adjustable and a 0 to minus 20 adjustable, and also 15 volts AC here and here. For this project that I happen to be working on, I actually needed 42 volts. So what I did is I took my minus 20 adjustable and I made that my ground going into here. And then I can adjust this so that it's actually at minus 19. That gives me my 19 volts. Then by running between my ground and the ground on here, which is now plus 19 volts, into a 7805, I've got 5 volts here. And then this other one here is going to the adjustable plus 20, which means I can vary between 0 and 20, which actually gives me from 19 to 39 volts, which is close enough for this project. And then if I put this into minus 12 here, minus 12 onto minus 19 gives me about 7 volts, which is what we're using to drive our op amp. It's actually a little less because of the adjustments right now, but we're using the 7 volts to drive our op amp. So what I'm going to do is I'm just going to measure those different voltages using this multimeter, and we should be able to watch the different adjustments, and you'll get an idea of where it's adjusting to. Alright, so now we have power to this unit, and it looks like it's readable there. So if I connect to my ground line here, and my output from the 7805, I should have roughly 5 volts. So we're at 4.95. That's pretty good for a 7805. Now if I go to here, which is the input into my op amp, 6.29 volts, 6.3. Okay, so that's what we're trying to drive the op amp at. Now if I measure to this input line up here, this was supposed to be 19 volts, or at 18.70. And now what I'm going to do is I'm going to hold this on to my plus one, and you can see right now we're sitting at 40 volts, and I can turn that down. You can see it adjusts fairly quickly, all the way down to 19.95. And that's the kind of adjustment we're looking for this project. So that seems to be working pretty good. Alright, so let's do a quick AC measurement. So I'll click it onto AC, and I'm just going to put this into the wall outlet. Right, you can see that. And there we go, 117.8. So power here should run between 110 and 120. 117.8 seems reasonable. We will look at the frequency ranges in that for AC shortly. Actually, why don't we see if it can detect the frequency of this wall outlet. 59.98. That's pretty good. They're at a 50% duty cycle. That's about what you'd expect from AC. Alright, so the next thing to do is go up here to the Ohms range, and we'll use this 100K pot, which I don't know if I can get both probes down into or not. Doesn't look like I can. Alright, so what we'll need to do can we do? We can try using these to see if they'll fit down in and give us a measurement. So let's see. 43K, so that's about halfway on that. Let's turn it all the way up. Or all the way down, as the case is. And we're at 33 ohms. That's pretty good. Go the other way. Full the other way, it should be about 100K. What have we got? 88.8K. So it seems to be measuring that fairly accurately. Alright, so this also has a frequency generator on it. So let's get some little tie lines out. And we'll take a look at that. Now let's see what it gives us. If we go to hertz. Let's see if we can measure anything. Okay, so according to that, we are at 8.39 kilohertz. And that's actually what I was using the other day for another project. So if I adjust the frequency, bring it all the way down to about 1 kilohertz, which is the bottom end of the 10 kilohertz range. So if I go down a range, now we're at 95 hertz, 12 hertz, 3.58, oh, or even lower. There we go. Not quite 1 hertz, which is where it's supposed to be. So now if I bring this up, I should be able to get all the way up to close to 10. Yeah, 11.85. So let's go the other way and see how high it'll go. 67 kilohertz. Yeah, that doesn't seem right. Definitely not. We should be in the kilohertz range. Yeah, 95, 94, that sounds about right. When you get too high, and she won't read it. Yeah, we're above its reading ability. 116 kilohertz. It's actually not doing too bad. 131 kilohertz, that's about right. Now it could be some of this amplitude if I give it a little more. There, it seems to be locking onto it better. 128 kilohertz is what it came up to, which is not bad. So that seems to work quite well. Now, right now that's on a sine wave. Let's see if we can do it for a triangle wave. Yep, and now we're a square wave. Yeah, that seems to be working pretty good. Let's take a look at the duty cycle. We expect it to be about 50% because I can't adjust the duty cycle on this. Yeah, so that seems to work quite well. Alright, so how about amps? Now, amps is a little more difficult to play with. What I'm going to do is I'm going to pause the video and I'm going to hook up my laptop, because this circuit right here is actually designed for controlling the output through this FET and across these resistors for different milliamp ranges, and that is the testing I was using it for. And to tell you the truth, it actually worked very well. It gave us very accurate readings. Actually, you know what? I'm not going to demonstrate that right now. What I want to do is I want to play a little bit with the other ranges. There's the backlight for him. What I want to do is I want to hook up my arbitrary waveform generator that I will be talking about in another video. But the arbitrary waveform generator should allow me to vary the duty cycle and amplitudes and frequency ranges just to see how accurately it picks up not just the frequency but also the RMS, because it does claim to be true RMS, so we need to check and see where it fits. As a matter of fact, why don't we put this on DC volts? And right now we're on a sine wave. Let's try the hertz range here. And let's bring this to about 60 hertz. So we're in the 100. Seems to be not adjusting down. It could be this board. So this doesn't seem to want to work with this, so we turn it back up to the hertz mode. Does it work here? No, we don't seem to be getting anything at all. Now, is it because I changed the hertz mode or what? Not sure what I've done here. Let's take this off and we'll reset it. Hertz in auto, and let's see if there's anything there it'll measure. Nothing. Alright, so what we're going to do is we're going to hook up my little multimeter, or my oscilloscope and arbitrary waveform generator. That's this one here, X-Protolab Plane by Gabotronics, and we'll hook that up and we'll see what we're actually seeing there. Now what I'm going to do is a video on the X-Protolab Plane in the future, because I'm doing a whole series actually. What I want to do is, because I'm an older guy with lots of kids and family, I can't afford to have a big fancy lab with all kinds of fancy lab quality gear and everything. But at the same time, I do like to do work for my electrical engineering course at home. So I'm trying to find the least expensive ways to do that work. And as you can see, I have this Discovery Lab that gives me a lot of capability, but not everybody can get one of those anymore. They don't make those anymore. And they're also, last time I looked them up, very expensive. So I'm looking for ways to make something with the same capabilities that doesn't cost as much. So I'd be interested in all you other home gamers, if there is requirements that you think would be advantageous, what you think those would be. Presently, what I'm working on is the idea of using two 24-volt AC-DC converters. So they'll take 110 volts AC and turn it into 24 volts DC. And that will allow me to modify it from there. And we can get one of the little modules that does constant voltage, constant current, constant power, and look at the voltages that we can get, hopefully basically recreating this board. So what I'd like to be able to do is have input in and have two 12-volt supplies that you can gang together, or two 24-volt supplies that you can gang together to get a maximum of 48 volts DC. And they'll put out 4 to 5 amps, which should be more than sufficient for most home uses, like home labs. And then if you have the like an LM7805 and 7812, that sort of thing, that are linear voltage regulators to bring it down to plus 12, minus 12, and the like, then we should be able to have a fairly capable home board. So what I've done here is I've just hooked up channel 1 of this little oscilloscope onto this little board, and I'm going to bring up the software. And what I'm going to do is I'm actually going to try and do a screen capture as well of what we're seeing. So just give me a second here to start recording the desktop. So I have the oscilloscope software up right now, and that should be recording. So this is just the default screen. As you can see, there is a signal here, and we're going to bring this gain down. Okay, so there we have a square wave that's actually quite high. So I'm going to go into the software options here, put it on automatic for channel 1, and it's going to automatically measure here. And you can see I've got a minus 10 to plus 10 at 20, so I have a 20 volt square wave. That's probably too much for the software in that little guy. So if I bring this down, let's see if we can get a 5 volt. Alright, so now that we're down to 5 volts, let's see if this will bring it up. It's not. Oh, actually, let me take a look at that scope again. When I put that on there, it shorts it out. Oh, I see why. You notice that? I still had it in amps. So of course it's not going to read anything. So, now that I have it in that mode, let's see. So it's saying 203 hertz. And if I grab my pointers here, actually I gotta, this, there we go. We'll trigger the display. And according to this, we're at about 200 hertz, which matches up. Now, you can see that as I move this, it goes from 200 hertz to 228 hertz. Okay, so if we change our range here, 205 hertz, which is a little more accurate. The reason that it jumps so much is because this is a digital scope, and as such, it only samples across here 256 samples. So that limits the values. That's why we get such a large step. You can get more accurate as you increase your range. So I'm just going to grab the trigger point over here so I can get a starting and ending value. And the closer in I get, see 202.5. So that's much closer to what we're seeing on this scope. So now that I've got it plugged into the right port, I'm curious as to what voltage is this will measure up to. So if I increase this voltage, it seems to top out, according to the scope, it just topped out at 20 volts, which actually makes sense given what we have here. This board being pretty old, I've already had a ground fault in it, so there's likely problems with this pot, so that it's not properly outputting. It probably is supposed to be a lot finer control than it is now. I haven't played with it in a long time. I actually had to build this as part of a course, which is pretty cool. So there we are. We have a 203 hertz square wave at 5 volts. So if we put that over here and we go on to AC, what does it tell us it's reading? 2.69 volts, which is not the 5.7 volts peak to peak, but RMS is based on frequency and area and on and off times and stuff. So I'm going to have to actually do the actual math on that. Let's change this over to a sine wave. And now the scope doesn't want to work on that. Let's change that. There we go. So I just used the auto set on the scope. So right now we have a 0.92 volt peak to peak. Let's increase that. I've been learning that because of this trigger on the triggering mode, if the trigger is outside of the range, like that, it can't trigger. So you'll notice this sometimes doesn't even update. But if I bring it down in the range, like that, I'll change this position to the center. Oh, look, it's an offset wave. Let's see if we can adjust that. So on the board here, I'm just adjusting the DC offset to try and center that a bit. That's roughly centered. Yeah, it'll probably change if I change the amplitude. There. It's roughly a 5 volt. And if we look at the peak to peak right now, there, we're at about 216 hertz. So let's see what this has to say. 203 again. So again, it's probably just the accuracy of the oscilloscope. But what I'm most interested in is what it sees this as for AC voltage. And what we'll do is we'll do the math on these later. There are some calculators that make it fairly easy. So right now it's saying 1.76 volts AC. And you can see the trace here on the scope. So what I'm going to do now is I'm actually going to stop using this one. We're going to unplug that. Like so. And I'm going to start using the arbitrary waveform generator in this little scope. Just right here. So right now all we're using is between the scope and that point there. Now, I really wish that I had gotten the banana clip sections for this meter, because then I could just clip these on very easily. But as you can see, I can't right now. Alright, so let us go into the arbitrary waveform generator. We'll start with an easy sine wave with a 50% duty cycle. Like so. 49.991, and we'll give it a full amplitude of 4 volts. And let's start at an easy range of, let's try 10 hertz. Alright, so I'll adjust my screen here. We'll ignore the vertical, actually let's just turn these vertical ones off. And right now it's measuring between 3.92 and 4 volts output there. And that's peak to peak, not RMS. So, if I look at this, what does it give me? It's giving me 1.41 volts. Alright, so let's change this up to 60 hertz. Okay, there's 60 hertz. This is the desired. The actual frequency is giving me a 60.038 according to the scope. And we are at a 50% duty cycle. Let's just open this up so it looks a little prettier. There. And you can see these little variations are part of it being a digital scope. And I know the guys on EEV blog don't like digital scopes, but for what it is, it's great. So let's see what this thinks of that. 1.411 volts, 60 hertz at 50% duty cycle. So let's start slewing that duty cycle. In here, I'm going to slew this down to roughly 20%. Okay, so you can see that it's not quite square, or not quite a sine wave. We're at 20%. Let's see what it gives me now. It should give me slightly different. 1.41. Alright, let's take it down to 5%. Let's see what that gives us. Also gives us 1.409, which is not too bad. So let's take this back up to 50%. Okay, and let's go to a square wave. Square wave, 4 volts, 50% duty cycle. And it's reading 1.98 volts. So now, if I take this duty cycle down to 20%, 19.99931, and I measure its RMS, we should have something different. Yeah, so we have 1.58. And let's go the other way up to 80%. Here's 80% duty cycle. We'll measure that. And we're at 1.596. Alright, now we're going to go and we're going to change this frequency. Let's jump this up to, right now we're at 600. 600 hertz, still at 4 volts peak to peak. Let's bring this down to a 50% duty cycle. Now really, we should see, no matter what the frequency is, we should see the same values across this. So we're getting 1.91. If we take this down to a 20% duty cycle, and we get 1.484. And now if we take it up to an 80% duty cycle, and we get 1.509. Alright, let's go one more range just for completeness. This is now up to 6 kilohertz. And you can see I'm starting to get a little fall off on the capacitors in the waveform generator. But let's take it back to 50%. 1.45. And we'll go to 20%. We are at 80.7 millivolts. You also notice the voltage has dropped off a bit in the average. The switching time is not quite getting up to full voltage before it's shutting off because of the 20% duty cycle. And we'll probably see the opposite effect at 80%. Because right here, yeah, it actually is getting shut off just long enough to detect it. I'm sure if I went up a little further we wouldn't quite see it. And we are measuring 91.9 millivolts. So some of that is probably the effect of the capacitor loading here. You can see the rise time and fall time, or the on time and off time, which is caused by capacitor charging. But some of it may be caused by the meter as well. But it seems we'll do the math, and then I'll post the results on that so we can see. Alright, so we are going to stop this. And we are going to stop the recording, if I can remember how. There it is. Alright, so while that's encoding over there, the last thing to look at on here is the temperature measurement. So it comes with this nice temperature probe, which I'm going to try not to touch with my hands, because right now it's cold out here. put it in there, put it on temperature, and select degrees Celsius and see what it says. According to that, it's 11 degrees in here. And if I warm it up on my hand, it says it's getting colder. That doesn't seem right now, does it? Is my hand cold? My hand's not that cold, so let's reset it, come back to it. Do I have it in backwards? Plus and minus. So let's turn it around this way. Oh, that looks better. So I did have it in backwards. The minus has to go into the common, and the plus goes into the red. So saying my hand is about 25 degrees right now, 26, and it'll warm up more. So if I just leave this sit here, we'll get a bit of the temperature that's out here. Meanwhile, I'm going to unplug this and move it out of the way, and we'll turn that off. Alright, so there we go. The basic AN8009 multimeter. It's smaller than I expected, because you've probably seen meters like this one around. Fairly cheap. You can actually get these for $3 on Banggood, and they're fairly small. This one is much larger. What you can see is much smaller than this, but you can see the display is much larger. It's actually very convenient to read. It's very nice to use with a board like this. I can just set it here. Very readable. It does have an auto time off feature, which I've actually found kind of annoying. If you don't touch it for a while, it will beep 3 times, and then if you don't touch it for a little while longer, it'll have one long beep and shut itself off. And that can be a little bit inconvenient. I seem to remember a video on YouTube where somebody was able to change the auto off time, so I'm going to look for that later. But for the home gamer, if you're looking for an inexpensive, fully featured, fairly accurate, and well packaged, well made multimeter, I don't think you can go wrong with the AN8009. The AN8008 still exists. You can still buy that around, and the prices on that are going down a little bit. You lose the non-contact voltage measurement, and you lose a couple ranges for capacitance, but you gain the square voltage creation, and you pay a little bit less. But a good multimeter is an investment as part of your lab. So I would say this is probably a good investment. I'd love to hear your comments on what you think a home lab should have. Like I said, right now I'm looking at building this part, a regulated power supply. Generally on a benchtop supply you only have one set of voltage ranges. Larger, more expensive ones have 2 sets. So that's what I'm going to try and recreate. I want to have 2 sets of voltages, a negative and a positive for a 24 volt and a negative and a positive for a 24 volt, and then have some of those digital voltage converters that will take the 24 volts and change it down to 0 to 24 volts, and also do constant current, constant voltage, and constant power. And then you can take the inputs, you could short the positive of one to the negative of the next and measure between the outside, and you'll have 48 volts to work with. Most of those units will handle up to 30, so that could be a problem. Also having a minus 12, plus 12, and plus 5 fixed voltage regulators that you could input into using whatever virtual ground you want, and to get voltages out that way, and also to look at other easy voltage provisions that you can make, like maybe a 3.3 volts. So if you guys want to tell me what kind of ranges you'd be interested in, that'd be great. And what I'll be doing is slowly building up a kit in a box this size with all the different supplies to do most of the electrical engineering stuff. I'm also looking at putting together some sort of electrical engineering course, right from the basics of electricity, what a resistor is, a capacitor is, and building up basic circuits on a breadboard like this, and also the computer engineering part based on these little nanos, but not using them through Arduino. There's plenty of Arduino tutorials out there, and there's a good set of STM ARM tutorials coming out, but there aren't any on AVR-C programming. And I think that these little modules, which you can get from Banggood for just over $3 Canadian, they're a 328p AVR module that's running at 16 megahertz, and it has tons of capability, and you can program them using open source tools and create all kinds of C programs. So what I'd like to do is go through C programming, do the basics of programming in C, data structures, that sort of thing, interfaces. Right now this is all running on the I2C bus, and how to use that, all using one of these little chips, but using C and actually doing basic level stuff, not using any of the Arduino programming tools, because that causes a lot of overhead in your code that slows everything down. We want to use these at full speed, because the ATmega chips actually at 16 megahertz, most of their operations it'll do in one clock cycle. So if you use C or even assembly, which is something else we can touch on, AVR assembly, then you get a lot more power out of these little chips. So let me know what you'd be interested in seeing, what kind of questions you'd like to see answered, and I'm going to see if I can build up courses for it and recommend parts that you can order to build up your home lab and home kit, and have a pretty fully featured electronics lab without getting too expensive. And as the start of that, I recommend the ANEng AN8009 multimeter. Thanks. I'll talk to you guys later.